This beacon symbolises the engineering achievements of the gold miners of the 1850s. Here on this remote Otago hillside, this wheel was used to power a stamper battery to crush gold-bearing quartz ore. But where on earth did the water come from to turn this 8-metre wheel here in Adams Gully?
Here, nearly 1,300 metres above sea level, above the snowline in many winters, water is brought through the Duffer Saddle over there. Miners used the same technique the Romans used 2,000 years ago, a gently sloping channel following the contours so the water surely and steadily moved along the hillsides. Crossing valleys on wooden flumes, which of course were not intended to last as long as the Roman viaducts. On reaching the water wheel, the weight of the falling water provided power for crushing rock. These water races, as they were called, not only provided water for stamping batteries, but were also essential to providing water for the winning of gold from the river valleys. Gold panning, or placer binding as it was known in California, led to the first discoveries in New Zealand. It was Gabriel Reed's experience in both California and Australia that led to his 1861 find in Gabriel's Gully. When the news reached Dunedin, 100 kilometres away, the town almost emptied. Gold was the magnet. As well as emptying towns, leaving farmers with no labour for harvest, it meant engineering works coming temporarily to a halt. The very men required to build the roads to the goldfields dashed off to join the search. In spite of labour difficulties, the road was pushed through that same year. It was certainly needed. The population of the area at around 12,000 persons was twice the size of Dunedin. Gold wasn't free out here. A lot of hard work and engineering skill was required to win alluvial gold out of these hillsides. When it comes to sluicing, not only do you need water, you need equipment to deal with the high pressures dropping the water from the races down onto the sluicing claims. Dunedin became the mechanical engineering capital of New Zealand in those early days. Water races to provide power for the Otago goldfields was one of the priorities given the fledgling Public Works Department formed in 1870. The government acknowledged that coordinated engineering assistance was necessary in exploiting the country's natural resources. In the South Island, most gold recovered was from alluvial sources. The gold was won from the rivers. But North Island gold is locked up in the rocks, and the crude stamping battery systems used in Otago were dwarfed by the huge mechanised operations here in the Coromandel. Imagine a large-scale operation using row upon row of machinery like this to crush the gold-bearing ore into a powder. Mechanisation like this required foundries and workshops, and Thames became the mechanical engineering capital of the North Island. Gold mining provided the country with valuable engineering expertise. In 1888, the Thames firm of A&G Price was able to erect on this site a 100 stamper unit for the Waihi Gold Mining Company. This was later extended to 200 stampers, one of the largest crushing batteries in the world. It was noisy, dusty, and inefficient. The first extraction system only recovered 45% of the gold. Then came the MacArthur Forest cyanide process. This Scottish development had its first field test here at this plant. Just as the government supported the South Island Water Race development for gold mining, it now went ahead and secured the patent rights for this new process. And here's how it worked.
The cyanide process dissolved the gold out of the powdered ore in huge cyanide slurry tanks like these. After filtering the gold-bearing liquid out, it was passed over a porous zinc sponge mass where the gold came out of solution. And then the gold particles were washed out and sent on to the refinery for melting into bars. Cyanide processing actually doubled the gold recovery rate from 45% to 90%.
The Martha mine at Waihi was the largest and most productive gold mine in New Zealand. From 1890 to its closure 62 years later, the 160 kilometres of tunnelled workings deep in the Martha Hill produced some 35.5 million ounces of gold.
Here we have another example of the association of water with gold mining. That building ruin up there is all that remains of the number 5 pump house. In its day, it housed a huge 52-ton pump driven by a 1,500 horsepower steam engine. The Martha mine was deep. Its workings extended over half a kilometre into the ground below me, and a major engineering task was keeping the mine free of water.
The pump was enormous by any scale. Every day it lifted from a shaft as deep as a 160-storey skyscraper as much water as would supply a town of 35,000 people.
Of course, there were gold mines right throughout the Coromandel, and here, some distance over the hills to the northeast of Waihi, are the remnants of the Queen of Beauty mine in Thames. These huge pump quadrants were rocked backwards and forwards by a massive steam engine in the building there. And as the shafts lifted up and down, they brought water up from the pumps below deep underground so it could flow away out to sea. You know, this is Victorian engineering at its best. Just look at the size of those large nuts on the top of the shaft.
Although New Zealand was half a world away from its Victorian origins, local engineers and craftsmen were well able to build machinery of comparable quality and performance. There's still gold beneath Waihi streets, and there's still gold in Martha Hill, lots of it. In spite of those 160 kilometres of workings down below, there was a limit to the amount tunnel mining could remove. So, is the remaining gold destined to remain here forever? Not if approval is given for the massive open-cast mining scheme currently being considered. It will involve digging out the whole inside of the hill and taking the rock and residue 3 kilometres across the valley to create a new set of hills. And what will be left after restoration works are complete in 30 years' time? A new lake nestled in the core of Martha Hill.
Of course, open cast mining is not new. It was pioneered in New Zealand by one of our major construction companies some 45 years ago. here to recover black gold in the Waikato, not far south of the Coromandel.
But coal mining history in New Zealand did not begin with the shallow open-cast mines in the Waikato. It began here on the isolated west coast of the South Island, where engineers played an important part in its development. High-grade bituminous coal was found buried deep in the hillsides, way up on the coastal plateau. The engineering problem was how to get it down for shipping out to the main centres of New Zealand.
Engineer surveyor R.B. Denniston discovered the coalfield named after him. Thomas Brown, an engineer trained in the coalfields of Northumberland and Britain, organised the work. And two engineer brothers, Henry and Robert Young, constructed the access to the Denniston coalfield up onto this plateau.
The Denniston incline comprised an endless cableway about 2 kilometres long, on which loaded coal wagons used their descending weight to haul up empty wagons. Seems a simple idea, but it was an engineering feat that attracted worldwide acclaim when it was opened in 1879. And during the 88 years of its operation, it lowered over 13 million tonnes of coal off the hillside down slopes almost as steep as 1-to-1. Whether it's by cableway or conveyor belt, the transport of coal is an activity that requires a lot of engineering input. Coal has been mined underground here in the Waikato for 120 years. But conventional coal mining gives a fairly poor return in terms of coal recovered. About 20% is the figure. The rest of the coal has to be left to hold up the roof of the mine. But if you can remove that roof from above, then you can get at 100% of the coal. It was the advent of large earth-moving machinery that made open-cast mining for coal economical. Mechanical engineers' development of steam shovels, then to diesel engine power systems, cut down the costs of muck shifting considerably. Up until mid-1986, the responsibility for overseeing the modernisation of the New Zealand coal industry has belonged to an engineer. Recent State Coal General Manager, Dr. Roger Blakely.
Well, the technology has gone 2 quantum leaps over the last 2 decades. In the early 1970s, state coal mines moved from the traditional mining era of hand shovels, power drillers, coal cutters, and so on, into the era of mechanised mining. And we brought in road heading machines, continuous miners, and they've been pretty effective. Now we're making the next quantum leap with the introduction of longwall mining technology, which we are introducing into the Huntly East mine in May 1987, and that will bring us right up to date with the state-of-the-art technology worldwide.
Roger, what benefits does the long walling equipment offer the coal industry?
Very important. The traditional board and pillar mining method is based on driving roadways through the coal seam in crosscuts. But you leave behind a pillar of coal, which may be 15 metres by 15 metres, to hold the ground up. And that means that you're only recovering about 20% of the coal seam. But the thing about longwall mining is that you can achieve a much greater coal recovery. The technique involves support of the ground by hydraulic supports to protect workmen while a shearer runs along the coal face and takes out a slice 2 to 3 metres high. And then progressively the supports move along and the ground collapses behind. Now what that means is that you can recover about 60% of the coal seam, and that you don't have to have the support of the ground, which can be very expensive in deep mines because it requires closely spaced steel arch supports. It does have environmental effects because it can cause subsidence of the ground above by up to 4 to 5 metres, which obviously requires careful environmental treatment. As far as open cast mining technology is concerned, in this mine here, the Weavers mine, we have introduced in New Zealand for the first time for coal mining a bucket wheel excavator. The contractor is bringing in what will be the largest bucket wheel excavator in New Zealand.
For the meantime, much of the coal from the underground pits goes to fuel the 1,000 megawatt Huntly Power Station, the largest thermal plant in New Zealand. Conveyors track across farmland to the power plant on the Waikato River.
This coal is not destined for Huntly. The power station is to use over the years some 70 million tonnes from the long hauling operation, deep underground. This coal is to be an important ingredient in another major New Zealand industry, one that has as its source of raw material the country's other black gold, iron sand. Iron sands for steel making. Hundreds of kilometres along the coastline, millions of tonnes of iron sand have been piled by the sea over thousands of years into huge black sand dunes. Sand that contains about 60% iron as iron oxide. As early as 1848, local engineers have been looking for ways of getting the iron out of this sand.
The Bessemer blast furnace process was under development at this time in Britain. Samples of New Zealand iron sands were taken to Sir Henry Bessemer in 1886 for an opinion on their potential. He personally carried out some experiments on them, but said that much research would be required before they could be commercially exploited. That research went on into the 1950s, much of it here at Glenbrook, south of Auckland. John Ingram, Managing Director for New Zealand Steel, describes a process of trial and error.
Well, the most recent failed attempt would be about the turn of the century, and a lot of work was done overseas in the meantime. The problem was recognised as the very viscous slag that produced when iron sand is smelted in the blast furnace. And so the oxygen had to be removed in the solid phase without melting it. And it was really, I guess, the rediscovery of the method the Japanese used centuries ago to make these samurai swords.
What contribution have engineers made to these developments?
Well, of course, they were closely involved all the way through. The plant we built was a prototype. This had never been used commercially before. The problems were many. The concentrate melted and stuck to the walls of the kiln, so we had solid blocks of iron to remove. We showered the countryside with black soot and iron sand concentrate. Those problems were substantially solved by a team of young engineers, New Zealand graduates who'd the company recruited right from the start, sent overseas for training. Those were the fellows that solved the problems. From the point of view of management, I think engineers are well suited to that task. They're trained in the economic production of things that people need, of services they need. They are used to managing men and materials. They must learn to manage money also, and must obtain a commercial sense. The least cost solution must be the one that they find. If engineers can do that, they can achieve anything.
The source of New Zealand Steel's iron sand is this open cast sand mine here at the mouth of the Waikato River. Since the mill opened in 1969, the iron sand concentrate from here has been moved by road transport 18 kilometres to the mill. But the planned expansion now underway will increase production fivefold. The problem is, how does one cope with the transport of these vastly increased tonnages of iron sand? 5 times more trucks? The answer is below the ground. Buried alongside this country road runs a pipeline that carries a mixture of iron sand concentrate and water quietly and speedily between the North Head mine and the mill. Simple solution, but one which required the firm of McConnell Dowell to overcome some thorny problems with a combination of engineering skills.
Well, the main problem, Ian, is that the iron sand is very heavy, and we have to pump it at high concentrations, which means that if we get it wrong and it settles out, which it'll do very quickly, then the pipeline blocks, and that is a bit difficult to clear.
What sort of engineering skills were combined to get this pipeline laid?
Oh, everything, starting with civil engineering on the route selection, with mechanical engineering involved with the joint particularly.
How do you protect the inside of the pipe from being worn away by the sand?
Well, that was probably the single biggest technological breakthrough on this line. We've got a line with urethane, it's a plastic, and the difficulty, of course, was to weld the line, which is necessary to maintain the strength, and not burn the lining off at the joints, which would allow scouring or wearing away of the metal.
The solution took the form of a special sleeve around each joint. The hollow in the sleeve was filled with a mist of water and air during welding. The lining stayed cool. This is another New Zealand steel iron sand operation 140 kilometres south of Auckland. 2 million tonnes of iron sand concentrate are exported from here each year to Japanese steelmakers. Now you may well ask, exported from where? Where are the roads, the railway, the harbour? Well, the new slurry pipeline at Glenbrook is an update on pipeline technology already in use here at Taharoa. Since 1971, these pumps have been pushing concentrate out to bulk ore carriers up to 130,000 tonnes in size waiting offshore. And that's not as simple as it sounds. New Zealand Technology has designed this harbour. It's a single mooring buoy anchored to the seabed. A submarine pipeline with a short flexible coupling to the buoy acts as the jetty. The ore carrier is connected to the buoy by floating hoses. The trick is that the whole system has to allow for wind and tide variations throughout the loading operation. Now the whole process has been taken a stage further. This plant near Westport is testing the feasibility of pumping coal from shore to ship. It could be an important development. Hemmed in by the stormy Tasman Sea and the Southern Alps, the west coast of the South Island has always had a transport problem. The harbours here are on flood-prone rivers which pour straight out of the mountains.
You can imagine the problems of trying to operate a port under those sort of conditions. Pumping of coal out to sea may be a 20th century solution, but to those Victorian engineers trying to provide reliable coal supplies to the rest of New Zealand, there was only one logical way, a way through the mountains behind them.